So today we will start a new topic, which is the kinetic theory of gases. So let us put the heading kinetic theory of gases. Kinetic theory of gases. So in this theory, that is in kinetic theory of gases, it is assumed that there are small molecules which are very large in numbers and they move in random direction in the gas. During the motion, they collide with each other and also they exert pressure on the wall of the container. So, to study the behavior of the molecules in a gas, two scientists, Maxwell and Boltzmann, derived the distribution law. And while they derived this distribution law, they have followed some assumptions. So, first we will see what are the assumptions of the kinetic theory of gases. So, let us write a subheading: Assumptions of kinetic theory of gases. Assumptions. So the first assumption is the molecules in the gas are very small, identical and non-interacting. Then second assumption is during the motion molecules collide with each other. This collision is elastic collision. This is the elastic collision. Perfectly elastic collision. Therefore, no change in kinetic energy of the molecule. Therefore, no change in kinetic energy of the molecule. Now the third is between two successive collision, molecule follow the straight path. And this straight path is known as the free path. This straight path is termed as free path. But between all the collision, the length of this free path is not equal. So suppose if we show the collision, then it is like this, the collision, and then it will change the direction, and then again the collision, it will change the direction. So these length are the free path, these lengths are the free path, but the length of free path is not equal between all the collision, and therefore the average of free path is known as, is termed as mean free path, is termed as mean free path, mean free path. And we will calculate the mean free path in some another lecture. Then come to the next assumption. During the collision, no force is exerted, between the molecules, the collision of molecules with the wall of the container, the collision of molecules with the wall of the container, results in the pressure on the wall, of the container, on the wall. And this pressure is, let us go to the next page. Now this pressure which is produced on the wall, this is proportional, or this is equal to, this pressure is the rate of change, of momentum, of particle or molecule, per unit surface area, So we can derive this equation, because we know that the pressure is equal to force per unit area, and if we use the second law of Newton's motion, then it is the force is equal to rate of change of momentum, dp by dt, rate of change of momentum per unit area, and therefore the pressure exerted on the wall of the container is the rate of change of momentum of molecules per unit surface area. Then the next, I think it is sixth, perhaps it is the sixth, let us check. Yes, it is the sixth point. Now the time taken, during the collision, is very small in comparison to the time between two successive collision, explosive collision. Or we can say that the time taken during the collision is very small in comparison to the time taken in traveling the free path. Both sentences have the same meaning. Now come to the next point. The molecules during their motion, the molecules during their motion, do not accumulate anywhere. Do not accumulate anywhere. Accumulate anywhere. Therefore, the density of gas is constant at every place in the container. Now come to the next point. The size of the molecule is very small or negligible in comparison to the volume of the container. In comparison to the volume of the container. And the next point, the intermolecular distance in the gas is large in comparison to intermolecular distance in solid and liquid. Therefore, in the gas, molecules can move freely in the whole space of the container. Now you know that in solid and liquid molecules are bind tightly and therefore they cannot move freely. In solid, the binding is more in comparison to liquid, and therefore in solid they can only vibrate about their mean position, and liquid this vibration is more, but in the gas the molecules can move freely inside the whole space of the container. So all these are the assumptions of the kinetic theory of gases, and Maxwell and Boltzmann, when they derived the distribution law, then they followed all these assumptions, and based on these assumptions they derived the distribution law. Now let us go to the next page. and then we will discuss two more small topics. So now put the heading Brownian motion. Put the heading Brownian motion. Brownian motion. So in Brownian motion, the particles move in zigzag direction. In zigzag direction, or in an irregular way, or in a random way. In a random way. In a random way. So in Brownian motion, the particles move in zigzag direction. During motion, they collide with each other. They collide with each other. And change their direction. Change their direction of motion. Their direction of motion. And this direction cannot be predicted. This direction of motion cannot be predicted. Cannot be predicted. So such type of motion is known as the Brownian motion. In kinetic theory of gases, molecules of the gas perform the Brownian motion. So such type of motion was first time observed by a scientist of botany. When he was studying some colloidal solution. Then he observed this type of motion, and on the name of the scientist, was Robert Brown. So on this name of scientist Robert Brown, this motion is termed as the Brownian motion. So Brownian motion is the zigzag motion. So as we have drawn the picture, so this type of motion where the direction is very random and irregular and one cannot predict in which direction the particle will move. So this type of motion is known as the Brownian motion. So now go to next topic, a small topic, which is the degree of freedom. So let us put the heading degree of freedom. Degree of freedom. Now degree of freedom is defined as the number of ways, a number of coordinates to specify the system. So number of coordinates to specify the system is termed as the degree of freedom. Or in another way, we can define the degree of freedom as the number of ways of independent motion. Number of ways of independent motion. Motion of the particle. Independent motion of the particle. So that is also known as the degree of freedom. So let us take one example. We will take three examples. In the first example, let us say it is the monoatomic molecule. Monoatomic molecule. Atomic molecule. So we have only one atom in the molecule. So for translational motion, one needs three directions. And these three directions are X, Y and Z direction. And these are the independent direction. Independent directions. Because we know that if the particle is moving in the X direction, then the motion in the X direction will not affect the motion in the Y direction as well as in the Z direction. Therefore, these three directions X, Y, Z are the independent direction. So in this case, the degree of freedom for the translational motion for a monoatomic case is 3. Now come to the another example and let us go to the next page. And we will take another example. So example 2. And here it is the diatomic molecule. Means H2, N2, O2, such type of molecules. So these are the linear molecules. Linear molecule. So to define the motion, we need three directions. We have three directions for translational motion. And what are these three directions? These three directions are the X, Y, Z direction. X, Y and Z direction. So these three directions are independent direction and they can define the translational motion. And we also have now the three directions for rotational motion. Now this molecule may rotate also. This can rotate along the X direction, Y direction or Z direction. It can rotate along three direction, X direction, Y direction and the Z direction. But the moment of inertia, if we say that this is the X direction, let us specify this, that this is the X direction. So the moment of inertia which is summation over mr square. So this moment of inertia is 0 along X direction. Where we have chosen the X direction along the line joining the two atoms. So when we will calculate the moment of inertia for such type of combination, then the r means the distance from the axis, and because we are choosing this as the axis of the rotation and the two atoms are lying on the axis, therefore the distance from the axis is 0, and therefore summation over mr square is equal to 0. So the moment of inertia is 0, therefore we will remove this rotational direction and we are left with only two direction. So we have the degree of freedom as, for diatomic molecule it is 3 translational motion and then 2 for the rotational motion, that is the 5 degree of freedom. Now let us take another example, example 3, and now it is for the polyatomic molecule. Atomic molecule means we have the number of molecules more than 2. So examples are methane and then ammonia, H2O, and there are many such examples. So here the moment of inertia along the x direction or in any direction is not 0. Along the x, y or z direction will not be 0 because the now the molecules are distributed in the different direction, and therefore the total degree of freedom is 3 for the translational motion, and the 3 degree of freedom for the rotational motion. So in total there are 6 degree of freedom for the polyatomic molecule. So now let us stop here, and in the next lecture we will derive the Maxwell-Boltzmann distribution law, and based on that distribution law we will calculate the various types of velocities, that is the most probable velocity, the average velocity, and also the root mean square velocity. So let us stop here.